Good morning, ladies and gentlemen. Welcome to Pre-Cal Notes number 10, Exponential Functions. No mistakes this time, I promise. Alright, our exponential functions are functions in this form, and notice where the x is, it's in the exponent right there. That's what makes it an exponential function. You may recognize A, B, H, and K. Those are going to be related to our transformations, which we will talk about on the back side of this paper. But very specific things, B cannot be 0 and B cannot be 1. If B were 0, nothing would happen. If B were 1, it would just be a constant function because that piece would just stay 1 the whole time. B is the base. That's the number that is raised to the exponent. That's kind of important to remember. We've got two types of exponential functions. We've got exponential growth. That one goes up. We've got exponential decay. That one goes down. When you talk about real life functions, anything that grows, increases, expands, blows up, talking about growth. Decay, decreasing, depreciates, descends, goes down. We're of course going to be talking about domain and range, and isn't that nice for both of these generic functions? We got arrows on both ends, so our domain is negative infinity to positive infinity. The range is 0 to infinity. We start at 0 and go up to positive infinity. Notice 0 is not included. We'll talk about that in just a minute. Then we've got the y-intercept. Both of these functions is 1. That will change. The x-intercept, none. We'll talk about that in a minute. Extrema, none. There is no change in the graph. It is always increasing or always decreasing, so therefore there is no change. No extrema. Not super important. You could probably forget that, but it's good to talk about these things because we already have, so we can relate them. Asymptote. Back again. This is just like the asymptotes in our hyperbolas. These functions will always approach but never touch this asymptote, and it is the x-axis. So there, imagine that dotted line on the x-axis. It's getting closer and closer and closer, going in the negative infinity direction for x, but it will never touch it. Over here, if we're going closer and closer to the positive infinity for x, but never touch it because it's an asymptote. This is why our range value, the 0 is not included. From 0, but not including 0 to infinity. And this is why there are no x-intercepts for these generic functions. However, our asymptotes can change. So, let's talk for a minute. I kind of skipped over this. Exponential growth happens when the base of your function b is bigger than 1. For example, if I had 2 to the x, that's going to grow. If I had 3 to the x, that's going to grow. Even if I had a fraction, 5 over 2 to the x, probably use parentheses on that so we don't get confused if it's just the 5 to the x or what it is, but this whole base is bigger than 1 to the x. Exponential decay, these are more typical fractions that are less than 1. 1/2 to the x, 1/3 to the x. You could probably even see a decimal, 0.5 to the x. Those are all less than 1. When you multiply by a number bigger than 1, it gets bigger. When you multiply by a number less than 1, it gets smaller. Growth versus decay. So let's see how some of these work. Take this first function here, f of x equals 3. Our b is bigger than 1, so we know it's growth. So we know it's going to be going up from left to right. Our asymptote, let's draw this in here so we don't accidentally cross it, is the x-axis. And then let's explore this one with a little table to see what happens. The first x values we're going to use are the easiest ones, most centered, -2, -1, 0, 1, and 2. And then I'm going to start in the middle just to remind us, actually I think I'm just going to start down here, just to remind us how these exponential functions work. Again, this is definitely Algebra 2 material, but it's important to review. When I plug in 2 here, it becomes 3 squared, which is 9. When I plug in 1 here, 3 to the first power is just 3. And when I plug in 0, 3 to the 0th power, don't forget that is 1. Anything to the 0 power is 1. That is saying how many 3's there are. So if there's a 0 there, there are 0 3's, but there's always that ninja 1 hanging out right there. That's where that 1 comes from. When our exponent is negative, that acts like a reciprocal. So 3 to the negative 1 is the same as 1 over 3. 3 to the negative 2 is the same as 1 over 9, because 3 to the 2 is 9, and if it's a negative, that acts as the reciprocal, flipping it, so 1 over 9. Graphing this, there's our y-intercept, 0, 1, 1, 3, 2, 3, 6, 9. Those ones you can graph perfectly, so we know it's going to go up. But then the second part, the lower ones, you just sort of estimate as best you can. But don't touch your x-axis, people, because that's an asymptote. Don't touch it. So negative 1, 1/3. Negative 1, get a little bit closer, 1/9. I know it's tricky. Be careful. Go really close, and it just goes on forever like this. Don't touch it! Mine, as you can see, kind of went up there, but it doesn't go up. It just goes closer and closer and closer to the x-axis. That's fine. You don't have to do any better than that. What's the domain? Of course, it's negative infinity to positive infinity. What's the range, you say? Oh, it's 0 to infinity, just like it was up here. Remember, that will probably change. What's the asymptote? It is the x-axis, or the equation y equals 0. All right. If you have any questions, pause it, talk to your friends. If not, let's go on to B. This one's definitely going to be decay. A little bit faster now. Here's our asymptote, the x-axis, y equals 0. Our table, x, y, -2, -1, 0, 1, 2. These are our go-to points right here. We're going to use these a lot unless it gets transformed in some way, and then we might change these. Probably not. I think what we're going to do is give you graphs, and then you're going to transform the already given graphs, so we're not going to have to worry about that. These will be the same when you are graphing on your own. Alright, so when I plug this in, this time, when I plug in 2 here, that 2 affects that, so it becomes 1/9. When I plug in 1 here, it stays 1/3. When I plug in 0, again, that 1 is sitting right there in front, so it's 0, 1. And then when I plug in the negatives here, it's going to flip this fraction, making it a bigger number. So -1 in the exponent makes this a 3. -2 squares it and then flips it, which is just 9. Very, very consistent pattern here. That's going to happen quite a bit. Okay, so you can make that connection and use those points. And this time it starts in the negative side as the high numbers, -2, 9, -1, 3, 0, 1, and then 1 1/3, 1 1/9, and then this time it comes down this way. Gets really close to the asymptote, but don't touch it! Decay. The domain is the same, the range is the same, the asymptote is the same for this function. Cool? Alright, this one has a little a value right there. Let's see what happens with it. Okay, we definitely know it's growth because our b value, this is b, that's b, this is a. So our b value is bigger than 1, so we know it's growth. Alright, let's see what happens here. X, y. Now pay attention when I fill out this table though. -2, -1, 0, 1, 2. When I plug in 2 here, 2 squared is 4, times 3 is 12. 2 to the 1 is 2, times 3 is 6. Okay? 2 to the 0 is 1, because that anything to 0 power is 1, but then times 3 is 3. So notice that relationship right there. That number in front, on these ones we had to drop in a 1, and there we got our 0, 1 y-intercept. When there's an a value, that a is also your y-intercept. you might put a note on there. A, in this case, y-intercept. Kind of helpful when graphing. Alright, and then negative 1 is going to make this a 1 over 2 times 3, 3 over 2. Negative 2 here makes it 1 over 2 squared, which is 1 over 4, times 3, 3 over 4. Okay? Those ones there are a little bit different because of that a value. So here's what we're going to do. Negative 2, 3/4, and again, that's not much different, but look at this. Negative 1, 3/2 is the same as 1.5. So you have to notice, graph carefully. It doesn't have to be perfect, but you do have to graph carefully. 0, 3, 1, 6, and then 2, 12 happily goes off of our graph. Don't touch the asymptote. Don't touch that asymptote. Don't touch that asymptote. Don't touch that asymptote. The asymptote didn't change, but what do you think this a value did in regards of transformations? That's right, it's a vertical stretch. We'll get to that next page. If you have any questions, turn and talk to your neighbor. Alright, this time writing the function when the graph is given. We know it looks like y equals something times something to the x. If I see here that my y-intercept is 1, that means that this value here is going to be 1, okay, because it's not changing anything. So b is what we're looking for. This is the number you multiply by. Okay? So let's make a table of these nice points. 0, 1, 1, 2, 2, 4. And nice points are the ones that cross exactly at those things. I don't need to worry about these negatives because they don't cross exactly. X, Y, 0, 1, 1, 2, 2, 4, 3, 8. And this is important to know. It's the number you multiply by on the y side, but your x side has to be consistent. Okay, so look for these consistent points. Plus 1, plus 1, plus 1. So as x increases by 1, y is going to multiply by what? 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. That's your b number right there. So it's y equals 1 times 2 to the x. However, we don't really write that 1, so it would just be y equals 2 to the x power. Okay? Or you could do it this way. Check this out. We know y equals b to the x. And again, you're only going to know that if it crosses the y-intercept at 1. Okay? Pick any random point. Like, for example, 2, 4. Don't pick 0, 1. That'd be silly. Y is 4. B is what we want to know. X is 2. So we're saying what squared is 4? B has to equal 2. That one's a little bit more complicated, but it'll get you there. And this property right here, we're going to use a bunch coming up next class. Logarithms. Alright, example 2. We've got this graph here. Let's make our table. X, Y. In this case, these are not my good points down here on the positive x's, so we're going to use negative 2, negative 1, and 0. Negative 2, negative 1, 0. Negative 2 is 1, 2, 3, 4. Negative 1 is 2. And 0 is 1. Our y is increasing by 1, so that's good. That means we can just figure out what we're multiplying by and use that. But notice, what type of function is this? Decay. It's decreasing, which means we're multiplying by a number smaller than 1. So one way to do this, if it's a nice fraction, like 1 over any number, is say, well, it's the same as dividing by 2, right? Which is the same as multiplying by 1/2. Okay? So notice that connection right there. That helps out a lot of people when they're trying to figure this out. If I can find a constant dividing pattern, put that number under 1, and that will work. 2 divided by 2 is 1, so it's really multiplying by 1/2. There's our b value. A is that 1, so therefore it's just y equals 1/2 to the x. Groovy kittens. Alright, let's talk about transformations. And here's the good news. Even though it looks funky, this is the same as a times f of b to the x minus h plus k, or c and d if you were in a different Algebra 2 class. And we already know how to do this. A is your reflection, vertical stretch, vertical compressions. B is your horizontal reflection, horizontal compression, horizontal stretch. H is your left and right movement. But remember, look, that's the opposite, okay? Just like these two bad boys are. K is your up and down. I highly recommend that you pause the video right now and fill in all the blanks around this. You can look at the notes online. You can try to do it from memory. It's the same transformations. Review it and use it. Because right here is how we use it. If I see this function, b is my base, it isn't going to act a whole lot on this besides the parent function, which we don't really compare to. This is going to be our parent function. Anytime we have exponentials, we're going to have this generic function, and it's got to have that same base. So we're saying f of x is 2 to the x, parent. Every one of these has a 2 to the x, so every one is changing in a different way. Plus 1, what does that do? Oh yeah, that's my k. That moves everything up 1. So just take all your points carefully. Up 1, up 1, up 1. Very carefully, up 1. And then do your best. And what do we not touch? Don't touch that asymptote. Don't touch that asymptote. B. We've got a -2, negative in front. That's our a value. When a is negative, it makes it a reflect over x, or a vertical reflection. So take every point, boom, over the x-axis. 1, 2, 3, 4. 1, 2, 3, 4. Boom. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Just a nice little mirror. But guess where our asymptote still is? It's still on that x-axis. Don't touch it. This bad boy, when we shift it, h, negative means to the right. Take every point, boom, 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 boom. Don't touch your asymptote. Boom. Easy peasy, lemon squeezy. Questions? Talk to your neighbors. Example 3. F of x equals e to the x. This is like pi. E is like pi. It's this random magical number. I forget how we get it, but you could Google it and it would tell you. It's awesome. But it works just like a number. So in this case, we're just practicing more transformations. E is given to you. E to the x is our base. So try these things, okay? Try A and try C first, and then we're going to take a look at B. Okay, now that you've tried A and C, here's how they worked. That 3x is our horizontal compression, which, now that we think about it, going back up here, that B should be right there. B is just our base. Okay, so I made one mistake. Sorry, Miss Clausen. That's just our base. That's our parent function. This is where the actual B is. Phew! Don't let that mess you up, kids. Okay, so that's what 3 is right here. That's our B, and because it's bigger than 1, makes it a horizontal compression, squishing in. If we multiply our x values by 1/3, we're just going to really estimate here. If this one's at 1-ish, here's 1/3-ish. This one's at 2-ish. 1/3 of 2 is 2/3-ish. Just kind of squeezes in. You don't have to be super accurate. The most important thing is knowing that this number is our b value, which makes it a horizontal compression. Okay, that's the important part. Knowing the transformations so that you can apply them to any function. C, this is a, bigger than 1, makes it a vertical stretch. So each piece goes up by 2. 0, 1 times 2 is still 0, 1, so that one stays right there. Careful if you're, yeah, that one stays right there. This one here is 0, 3, goes up to 1, 3, goes up to 1, 6, and it just gets really stretchy that way. So that 2 makes it a vertical stretch. Alright, this one here is where we're going to talk about, and it's going to lead us into this bad boy, our next last part, horizontal asymptotes. The negative here makes it, if b is negative, it makes it reflect over the horizontal, okay, or horizontal reflection, which means reflect over y. So it's just going to flip and switch around. And if you think about it, that makes this a negative, so it reciprocals all of our fractions, which if they were negatives over here, then they would flip sides. So that kind of makes a lot of sense when you think about the math. So let's do that one just really quickly and lightly to see what's going to happen next. That one stays there. So it's going to look like this, just based upon the reflection. But then what does this do? It shifts it down 1. So that reflection and then down 1. This is our real one. What did that just do? What did that just do? Oh, you guys are going to freak out. Oh no, I just crossed the x-axis. Why? Because this shift down also shifted our asymptote. Alright, so there's the big connection. This shift down shifted our asymptote from y equals 0 to y equals -1. So this has a new asymptote. And that's what we're doing right here. Determine the equation for the asymptote for the following. These all look super complicated, right? The asymptote is based upon that k value. +1 means it moves up 1, which means our asymptote equals y equals 1. The asymptote was at y equals 0, shifted up 1, y equals 1. Down 5, the asymptote is y equals -5. Careful now, this k is not in the back, it's in the front, but it's +4. The asymptote, y equals 4. You do this one. Pause. Now that you've done it, you're right. The asymptote, y equals 3. Good job, everybody. Now there's one last thing. When we shift the asymptote, it changes the range. It changes the range. Instead of being 0 to infinity, this one is now 1 to infinity. Instead of being -5 to infinity, or sorry, 0 to infinity, this one is now -5 to infinity. Instead of being 0 to infinity, this one's now 4 to infinity. And then be careful on this last one. What else happened here? Reflection over x, which means it now is up 3. Here's our asymptote, but it's going this way. Paying attention is helpful. So this range is -infinity to 3. Alright? Be very, very careful. Your horizontal asymptotes affect the range. So does reflection. Booyah. I think your domain is always negative infinity to positive infinity. That's all I got to say, kids. If you're confused, go to tutorials, please.